One sec, guys, sorry. All right. Hey guys, welcome everyone. Thanks for being here. Today is the first Nexus MedTech workshop. We'll be covering cardiovascular devices. Can I get you guys all to scan this QR code just to register your attendance? And it might come in handy later if you come every week. We might have some other events which unfortunately are going to be restricted in terms of numbers. But if you come every week, you guys will be top of the list. So please just make sure you fill it out. Essentially, the goal of these workshops will be to give you a technical perspective of medical technology, because you'll hear a lot about it during your course studying medicine, but it's all from like a clinical perspective. And so we're interested in teaching you kind of how these devices work, talking about the current state of the art, and then also the emerging technologies that are coming, where the fields are moving towards. And hopefully through that, we can get you all interested in MedTech, because it is definitely an unusual pathway for medical students. And there will be some questions throughout. I would appreciate if you guys try to engage and shout out your answers. Feel free to discuss them amongst yourselves too before you shout them out. But as we always say, like, no silly questions, no silly answers. Ask questions. Try and track with some of those answers. Everyone done scanning? Anyone still going? No? All right. Let's get going. So just a bit about me. So I'm a final year medical student. I did my honours last year at the Victorian Heart Hospital at a lab called Create Lab, which is a cardiovascular engineering lab. My project was the fabrication of a compliant aortic phantom, which you can see here. Essentially just a model of the aorta that they use for research. I have an interest in engineering, more particularly hardware, so design, manufacturing, and more recently, physical AI. And I'm a researcher and TA at the Monash Medical Technology Lab. So tonight we're going to be doing a little overview of cardiac anatomy and physiology. That's because we've got some first years here. Can I get an idea of what year levels everyone is in? So if you're in your first year, can you put your hand up? All right, second year? Third years? Any fourth years? Fifth years? Nice. Any BMed size, MPH, PhD, any of them? No. All right, cool. So a few first years here. So we'll just try and cover whatever's like kind of relevant for the devices. We won't labor on the anatomy and physiology too much. And then we'll go through electrical devices, valve replacements, PCIs. We'll talk about more about what that is for your first years, and then finish off with mechanical support devices, including probably my favorite part of tonight, which would be the total artificial heart. All right, so just to break down the heart, I like to think of it as a machine that the primary function is to pump blood. So it's a mechanical pump. It has some valves which prevent blood from flowing in the wrong direction, an electrical system which coordinates all of that, and finally a fuel and weights transport system. So when we're talking about the mechanical pump, what we're really referring to is the muscle that surrounds the heart, so the myocardium, which is surrounding four chambers. So we've got our right atrium, our right ventricle, the left atrium, and the left ventricle. So the right side of the heart is predominantly working with deoxygenated blood. So when your muscles use up that oxygen, that blood then flows back into the right side of the heart, starting with the right atrium. It gets pushed down to the right ventricle and then pumped out to the lungs via the pulmonary artery, so the artery that goes to the lungs. And at that point, it gets oxygenated again, comes back into the left atrium, and then gets pushed down to the left ventricle, which then is actually the biggest part of the heart, and that pumps all that oxygenated blood around the body. So when we have a problem with our mechanical pump, we get something called heart failure. And this can change the muscle and the size of the chambers. And when we put all this together, we get the cardiac cycle. So we can say it starts with diastole, when the heart isn't doing anything, so it's at rest. And during that time, you've got blood flowing in from the veins into both the atria, and then some of it's also flowing down into the ventricle. Then you get atrial systole, so the atria both contract, pushing whatever's left in the atria down into the ventricles. And then after that, you have ventricular systole, pushing all that blood out of the heart to the lungs and to the rest of the body. So at the outlet of each chamber, we have a valve, and the point of the valve is to prevent blood from flowing in the wrong direction, and it is the closing of the valves which are responsible for the heart sounds. So the way that fluid moves is that it moves from high to low pressure. And so if we take the example of the left ventricle, which pumps blood into the aorta, when the left ventricle contracts, it increases the pressure inside the left ventricle, and that pressure ends up exceeding the pressure in the aorta. That's why fluid then moves from the left ventricle into the aorta, and at the same time the leaflets of the valve will open, ejecting a laminar ejection of blood through the valve. So as that blood moves through, the pressure in the aorta ends up increasing until a point at which it exceeds the pressure inside the ventricle. And at that point, blood now still moving from high to low will want to move backwards. And at that point, the leaflets of the valve will close, preventing any blood from leaking through. And so the problems that you can get with the valves are essentially either it's not going to open properly, so stenosis, where you'll have limited blood flowing out, or you can get the opposite, where it's not closing properly, so regurgitation, and this causes leakage of blood in the wrong direction. Now, coordinating all of this contraction of the atria and the ventricles is the electrical system of the heart. And so it starts with the sinoatrial node. So the heart is able to initiate its own electrical impulses. It doesn't require the brain to send some sort of nerve impulse down. It's got its own cells called pacemaker cells, which will auto-initiate this electrical impulse. And usually that starts up here in the sinoatrial node. So when that electrical impulse is sent off, that causes contraction of both the atria. That impulse then travels down to the AV node, and then down into the bundle of His, splits off into the left and right bundles and into Purkinje fibers. And once it reaches this bottom part here, that will cause the contraction of the ventricles. So therefore you get the atria contracting first, followed by the ventricles. Now it's important to know that it's not just the SA node that can auto-initiate its electrical impulses, it's actually all of the components of the electrical system, but the SA node is the fastest. And therefore, the SA node is what actually drives the heart rate. But you can have problems with any part of any part of the electrical system. So for example, if the SA node stops working, you've got a backup, which is the AV node, the next fastest one. And sometimes if the AV node stops working, then you're not getting that impulse traveling from the atria into the ventricles. So the atria will beat at 60 to 100 beats per minute, but the ventricles will be much slower because they will be coordinated by either one of the bundle of His or the Purkinje fibers. And so those are some of the common pathologies that we see, so we can have trouble with any of the electrical system. And I'll bring your attention specifically to SA node and AV node dysfunction because those are often treated with pacemakers, as well as the last few here, which are called shockable rhythms. So you use either cardioversion or defibrillation to fix them. And we'll talk about those devices later. And finally, the fuel, waste, and transport system, essentially I'm referring to the coronary arteries and veins. And the main problem that you can get is narrowing of the coronary arteries, which is called stenosis. And then when you have that narrowing, you have a decrease in blood flow reaching the myocardium. That loss of oxygen causes a chest pain called angina. And if you get a complete blockage of those arteries, you get a heart attack, otherwise known as an acute myocardial infarction. So, firstly, going into electrical devices, starting with the ECG. So the point of the ECG is that it measures the electrical activity of the heart. And a standard ECG has 10 electrodes, one on each arm, one on each leg, and then 6 across the chest. Now these are all connected to 10 leads, and I'll just note that the leads are the wires in this case, because that can get a bit confusing with ECGs normally being called 12 leads. Those 12 leads actually refer to the views in which you view the heart. So the way the ECG then has a look at the electrical activity is that it calculates the potential difference between two separate electrodes. So for example, if you look at the first lead, lead 1, that actually looks at the electrical activity traveling from the right arm to the left arm. So it captures any electrical activity that's moving in this direction. And so then you can do that in multiple different directions until you end up with 12 different views or 12 different leads for an ECG. And so that's how you end up with these 12, AVL, AVF, AVR, 1, 2, 3, and then V1 to 6 across the front. and they end up with an ECG trace like this, which you'll all learn to interpret at some point. All right, so then we have the pacemaker, which is one of the most common electrical devices used in cardiology. So the point of it is to restore normal activity of the heart. It's made up of a pulse generator as well as these leads here that lead to an electrode, and these electrodes are placed inside the heart. And so the pulse generator goes just below the clavicle on the left-hand side normally, and those leads will go through the veins into the right side of the heart. They also have a lithium-ion battery, which usually can last 5 to 10 years, so just keep that in mind for later. So then the pacemaker has a few different functions. First of all, it needs to be able to sense the cardiac activity. So it needs to be able to sense when the atria is contracting and when the ventricles are contracting, because that's how it knows if the heart is properly functioning. Then if it is functioning or isn't functioning, it can then trigger or inhibit pacing. So for example, if you have a heart that is, say, an SA node that is not working properly, so the heart rate is normally too slow, then you will have a pacemaker that is constantly keeping it going, say, above 60 beats per minute. But then for some reason, if the heart on its own is able to beat faster than that, you will get the pacemaker sensing that ability of the heart to pace faster, and then it will inhibit the pacing that it was doing so that it will allow the heart to take over the rate, the rate at which it's beating. So the leads can be either unipolar or bipolar. So if it's unipolar, it's got an anode and a cathode, with an anode in the pulse generator and a cathode at the tip, while bipolar has both the anode and the cathode in the tip, so that's both are inside the heart. So the problem with a unipolar one is that because you've got an electrical current that is moving all the way down from the pulse generator to the cathode, that means there's an electrical current going from under the clavicle all the way to the heart. And so you can get interaction with other electrical activity in the body, so we tend to prefer the bipolar leads. All right, so you can have a pacemaker that goes just into the right atrium and right ventricle, which is a single chamber. You can have dual chamber, which go into the right atrium and right ventricle. You can also have one that is biventricular, or otherwise known as cardiac resynchronization therapy, or CRT, and that goes into both of the chambers in the right side as well as the left ventricle. Does anyone have any idea which one is the most commonly used? Hands up for single chamber. Hands up for dual chamber. Hands up for CRT. Cool. So it's generally the dual chamber ones that get used. And the main reason for that is essentially you're able to both sense and pace both the atria and the ventricles. You just have a bit more control. So even if you only really need to pace one or the other, you just have a bit more flexibility with if something else goes wrong, you're going to sense it because you have a sensor in both the atria and the ventricles, and you can adjust accordingly with electrodes in both. Now, CRT is an interesting case, so that's only used for heart failure pretty much. And that's the reason for that is that when you have just a lead in the right ventricle in heart failure, there's often a slowing in conduction going towards the left. So when the right is paced, you end up seeing that the right ventricle contracts a little bit before the left. So you have a desynchrony between the ventricles, which wouldn't happen if you don't have heart failure. And so you need that extra lead in the left, which will actually make sure both the left and the right contract at the same time. So a question for you guys is, what do you think are some of the problems with a traditional pacemaker? You might be aware of some of the innovations in pacemakers as well. Like what would we want to improve on in the design of pacemakers? And feel free to discuss that amongst yourselves and throw out any ideas. All right. Anyone want to throw out any ideas? Yeah, go for it. Yeah, nice. Any other ideas as well? You ready? Yeah, that's a good thing. We'll touch on that. Yeah.
I think generally what adding on MRI just can't be anywhere near that.
Yeah. Does anyone know why MRIs or magnets can be problematic for pacemakers? Say again? No. Okay. All right, well, those are some good points, and we'll try and discuss some of them. Okay, so the first one is, yes. So traditional pacemakers were not safe for MRIs. The modern ones actually are. And that's for two reasons. First of all, if you have any magnetic materials in them, they're going to interact with the MRI. The second thing is, and some of you guys might have learned this in like high school physics or something like that, if you have a magnet that is moving around a wire, you get you can get an electrical current that is induced in the wire. So if you already have an electrical current that's pacing someone's heart, you don't want to interfere with that. So that can be quite problematic. And so the way you solve that is, first of all, of course, use non-ferrous materials. So non-ferrous meaning like not containing iron, so they won't be magnetic. And you also have special casing and insulation for the wires that prevent electromagnetic interference. But that's something that's kind of been solved for a while now. So the next problem is actually the leads. So leads can get infected, they can fail, they can cause venous obstruction because they're going through the veins. And so the solution that a lot of people have been working on recently is the leadless pacemaker. So the leadless pacemaker gets directly put into the heart. Normally it's only a single chamber one that goes right into the right ventricle. Now ideally you would also have dual chamber leadless pacemakers, but then the problem is you need to be able to coordinate the two. And because there's no wires, you've got to do that wirelessly, and I guess the heart contraction is quite it's quite important to make sure we get that right. So I think that'll be something that does come eventually, but it's not something that exists at the moment. Kind of the intermediate step that they have is, instead of being able to measure the electrical activity of the atria, this one here, when it's in the right ventricle, has an accelerometer that can sense vibrations. So it can, in theory, sense the vibration of the atria and therefore coordinate the ventricular contraction alongside the atria. Now, I guess another question is then, like, how do you power a leadless pacemaker, right? So it might have a battery inside it, but what do you need to do if you want to replace the battery? So I guess one possibility is you could look into wireless charging systems as well. But another thing that's been kind of thrown out recently is using piezoelectric energy harvesting. And what that is essentially it converts vibrations into electricity. And so the idea with this company, KDAC, is that they want to convert the vibration of the heart itself, so the heart's pumping, into electricity. And so in theory, they say that they can have an indefinitely long working pacemaker. All right, and then getting into cardioversion and defibrillation. So these are the two kinds of shocks that we can use. Cardioversion is used for stable arrhythmias, so things like atrial fibrillation. And the idea is that it synchronizes the shock with the beating of the heart. So it does actually take into account what the electrical activity looks like right now and applies a lower energy shock, while defibrillation essentially just wants to reset the heart. So it's used for more unstable arrhythmias when people, if it's not treated, they're going to die, while cardioversion can be kind of planned out and done in the future. Well, yeah, with defibrillation, essentially just going to shock them with higher energy. It doesn't matter where in the cardiac cycle it is, because you're just trying to reset the cardiac cycle. And so to do that, you have an ICD, which can be implanted, again, just like a pacemaker, with a pulse generator underneath the clavicle, leads going into the right ventricle, plus minus the right atrium. They can also pace, in which case each of these two leads will just have two wires running inside them with two connections to the heart. And one is able to provide a higher electricity shock for defibrillation, and one is able to provide lower energy input as well, which would just be pacing. And currently there's no leadless technology that exists, but I suspect you could probably go down a similar route and produce something that is leadless as well. All right, so next up is valve replacements. So there's two kind of main types of valves. There's mechanical valves and bioprosthetic valves. Historically, the oldest ones are the mechanical valves, which were originally the ball and cage design, which you can see here. So the ball and cage is essentially, you've got blood flowing in from the top there, and it pushes the ball down into the cage. As the pressure increases on the other side, it ends up pushing the ball back, and it blocks off that entrance. So you can see how it's a valve preventing flow going the other way. The tilting disc here is slightly different in that when it pushes through, the disc tilts, and then when the pressure increases on the other side, the disc is then pushed back up, preventing flow in the opposite direction. Now, thinking about how blood flows in our human native valves, anyone got any ideas as to what might be problematic in some of these valve designs? Again, feel free to discuss that and get back in a moment. So think about even where blood flows in the human valves versus where blood will flow in these valves. Think about what are the problems, like what are we worried about forming inside the heart if things aren't flowing nicely. All right, anyone want to throw in any ideas? Sure. Yeah. Yeah, that's a fair point. If you use this for the aortic valve, that wouldn't work. Good. Any other thoughts? You guys are discussing some stuff here. Yeah, that's a good point. Yeah. Anyone else? Go for it. Is it the what's that? Okay. Yeah, nice. So I guess I was thinking it down a little bit of a different path, but I'm thinking primarily about the hemodynamics of it. So if you think about this ball in soccer, right? The ball is in the middle, so you end up getting blood flowing around the sides. But if you have a regular valve, all the blood is flowing nicely straight through the middle. You get that laminar flow through the middle. Well, on this one, and even this one, it's asymmetrical. The blood flow is turbulent. When you have turbulent blood flow, you can get damage to the red blood cells, so hemolysis. You can also get blood stuck in some of these joints. You can get it stuck behind the ball here. And if blood gets stuck, what happens? Yeah, exactly. So we can get clots. So we have an increased risk of thrombosis. So neither of these are in use today. So the modern design is a bi-leaflet design. So you can see that when these leaflets open, there's actually very little resistance to blood flowing. And that's something I should have mentioned previously. There's a lot of resistance to the blood flowing, especially in the ball design, because it's essentially taking up a lot of that space. So there's way less resistance in this. There's pretty laminar flow moving through the middle that decreases your risk of thrombosis, decreases your risk of hemolysis. Yeah, and so then the central part, the leaflets, are made from a plastic of pyrolytic carbon. Then you've got a titanium casing around the side and a suture ring so that the surgeons can actually suture it into whether it be the aorta or to where the mitral valve is, for example. Okay, so then the alternative is the bioprosthetic valve. So when we say bioprosthetic, essentially we're using living tissue that's been treated to make a valve. So in the case of the porcine aortic valve, this is directly just an aortic valve taken from a pig that's implanted in a human, while the bovine pericardial valve takes pericardium, so the kind of lining of the outside of the heart, and they form it into the shape of a valve and implant that. So normally with implantation, it can be done, they can all really be done surgically. But I guess the newer thing is to do a transcatheter, so a transcatheter aortic valve replacement, for example. So that essentially is putting in a tube that, say, goes into a artery in the groin, and they essentially fold up the valve and they push it up that tube and then into the kind of outlet of the aorta, which is where the aortic valve sits. So if you think about that, you need to be able to compress the valve. And so if you have a mechanical valve that's made of plastic and metal that is like a metal ring rather than kind of something nice like this, which you can squish up, you essentially can't use a mechanical valve for TAVI procedures, but you can use bioprosthetic valves. So in comparison, the mechanical valves, while being much more durable, can last longer. They require long-term anticoagulation because they are still like a foreign object inside the body, while the bioprosthetic valves don't require lifelong anticoagulation, and they can also be implanted using those transcatheter procedures. So it would be much more suitable for people who, for example, can't get surgery. Go ahead.
With the bioprosthetic
Reasonable question. I don't know, to be honest, but I know that it is treated with something. So, yeah, but I don't know. That's a good question. All right. And so some of the innovations with valves is, well, one of the newest things is you using something called polyurethane or other polymers to make valves. Now, the good thing about these things is that, first of all, they don't require the lifelong anticoagulation, but they do have the durability of a mechanical valve. And so, and then they're also like quite a soft material, so you can squash them up and use them for TAVR as well. And they're manufactured using injection or dip molding, as well as 3D printing. And if you're interested to hear more about those things, feel free to come have a chat to me afterwards. And the other option is your tissue engineered valves. So these are really new. They use the patient's own cells, often either stem cells or endothelial cells, and they grow them over a biodegradable scaffold inside a bioreactor, which is able to mimic kind of the internal human environment. So it has oxygen, nutrients, it has blood, that's all blood-like fluid that is flowing in it, so it can kind of stimulate the valve to grow. And then, in theory, it should also be able to grow with a patient when you implant it into the patient, because it will integrate into their heart. And so it should be ideal for pediatric patients. All right, so next up is PCIs. So PCI is generally used for restoring cardiac blood flow. It's done transcatheter, so just like the valve replacement, it's either through the radial artery or through the femoral artery, and you move the catheter all the way up through the aorta. Sorry, not through the aorta, to the end of the aorta where the entrance of the coronary vessels are, and then into the coronary vessels. You use a guide wire to get to the exact site, and then there's a couple of different things you can do. You can either put a balloon in and that expands and then kind of presses the plaque to the sides. You can put in a stent that then holds it open. You can also do atherectomy, which will kind of shave down the plaque. And we'll talk through each of those three. And so starting with the catheter, it's a 2 millimeter polymer tube that is used for delivering tools, and it's used for a variety of procedures. And the guide wire, interestingly, is I think the most interesting part about it is that it's steerable in that you can convert one-to-one torque. So essentially, when you turn one end of it, the other end should turn by the same number of degrees. So if you turn one end 180 degrees, the other end should turn 180 degrees as well. And it has like a little bent tip, so that essentially when you turn it, you can change the direction in which it's facing, and then when you push it a little bit further, it'll then follow that direction into whatever vessel you're trying to get into. So then for the balloons, essentially it's like a plastic balloon that you fill up with some sort of liquid, probably saline, and it's inflated by a little special type of syringe called an indeflator. The interesting thing about that is that it doesn't work in the normal way that a syringe works, in which you just push and pull a plunger. It instead has a thread. And what the cool thing about the thread is that if you turn the thread, say 360 degrees, that's a big movement for you, but the thread only moves up by the thickness of one thread for each revolution. And so you can much more precisely control the pressure inside the balloon. And then finally, stents, we've got three types: bare metal, drug-eluting, and bioabsorbable. So the bare metal stents, allows more inflammation in that when you put a stent in, essentially it damages kind of the inside of the vessel, and then you're going to want the endothelium is going to try and grow, and often it'll grow, well, not often, sometimes it will grow into the stent itself, and so you can get restenosis inside the stent, so you just get growth into the stent, and that's obviously a problem. And so the way you prevent that is using a drug-eluting stent, which is the preference usually. And so the drugs in there, so it's not like an anticoagulant or anything like that that'll prevent clotting. It's supposed to slow down that healing process so that you don't get that healing directly into the inside of the stent, causing stenosis. But because it takes longer, you also have a longer risk of thrombosis where you can get a clot inside it, and so you have to take longer anticoagulants if you get a drug-eluting stent. The bioabsorbable stent, in theory, disappears after a certain amount of time, but it has a high risk of thrombosis, so it isn't really used that much yet. So the point of atherectomy is to remove any really calcified lesions. So sometimes the balloon isn't enough to be able to push it out the way and open up the vessel. So it has a diamond-tipped burr that essentially works like a drill and just kind of passes straight through and turns the calcified plaque into really small particles that do end up moving down, but they don't cause any sort of clots kind of further down because they're so small. And it doesn't really damage the vessel walls. Does anyone know why they use diamond? And you might have seen diamond used for other things like cutting glass, for example. Does anyone? Yeah, go ahead. Sorry? There is calcification of the artery, yeah. Yeah, the diamond cut through it, yeah. But any particular reason why we might use diamond over other things? Yeah, anything else? So the special thing about diamond is that it's pretty much the strongest natural material that there is. And so it doesn't get blunt with use, and it's pretty much guaranteed to get through the plaque. The other thing, it's got high thermal conductivity. And the reason that that's important is because when you're drilling through something like this, that's a lot of friction, and friction creates heat. But because it's thermally conductive, it can absorb a lot of that heat, so the heat doesn't get dissipated to the surrounding tissue and damage that tissue. Now, another type is the orbital atherectomy, which, I don't know, I think it looks kind of funny, but essentially it's like if you have a string and then you put a weight in the middle and you're kind of flinging it around. And so it's kind of like scraping the inside of the vessel, again, using a diamond-coated crown. And the third type is laser atherectomy, which is able to kind of vaporize the plaque using a specific wavelength which targets the plaque over the vessel wall, and it's normally in the UV range. Okay, now getting on to mechanical support devices. So, before we go into total artificial heart, we'll talk about ventricular assist devices. So these can be used for both the left and the right ventricle, or both at the same time. And generally they're used for three purposes. One is bridge to transplant. So if someone's waiting on a transplant, they can get this temporarily to help the function of their heart. It can be used as destination therapy, in which they're just going to have that for the rest of their life. Or sometimes even bridge to recovery, which I found quite interesting in that it's if someone has really acute heart failure due to something, that they can get this device in until they recover, and they can actually take it out. And seemingly the heart is able to recover, because it does actually create a hole in here inside the ventricle. And so the way it works is there's a hole in the ventricle that the blood is sucked through, and then it's pushed out via this tube directly into the aorta. So instead of helping the ventricle contract, it actually takes the blood out of the ventricle through an alternative path and takes it to the relevant artery. And so that has an external controller and battery pack that the patient have to carry around. And so then coming to the total artificial heart, this is generally for end-stage heart failure. Again, can be used for bridging to transplant, or ideally for destination therapy, as well as what the future is moving towards. And older designs attempted to mimic the pumping of this heart. So for example, this one had separate pneumatic pumps that were supposed to represent the two ventricles. But the one I'm more interested in talking about is the BiVACOR total artificial heart. Did anyone see this on the news recently? Some nods, yeah. Can I get you guys to scan this QR code? it's going to come up with a 3D model that you guys can kind of like play around with as we're talking through this, because it'd be great to be able to see the kind of different views of it. Cool. All right. So, the BiVACOR total artificial heart is made up of 3 components: the pump, the controller, and the driveline. So the pump is the actual kind of heart part that actually goes into the chest. The controller is what sits on the outside and has all the electronics and has some rechargeable batteries. And it also has a driveline, which is essentially just the wires that connect the two. So there's a wire coming from the outside, one from the inside, and they have a little connector in the middle. So the pump is made up of, again, 2 sides of the heart. So you've got an inlet for the left-hand side and an inlet from the right-hand side. And then it uses a centrifugal pump, which is run by this one impeller. So it's like a rotor in the middle. I've got a little video here on how impellers actually work.
There are many types of impeller, but most will have these backward curved vanes which will either be open, semi-open, or closed with some shrouds. These backward curved vanes do not push the water. The curves rotate, with the outer edge moving in the direction of the expanding volute. These vanes will provide the fluid with a smooth path for the water to flow. We'll see that a little later in this video. The impeller is submerged in water. When the impeller rotates, the water within the impeller also rotates. As the water rotates, the liquid is radially pushed out in all directions to the edge of the impeller and into the balloon. As the water moves outwards off the impeller, it creates a region of low pressure which pulls more water in through the suction inlet. The water enters into the eye of the impeller and is trapped there between the blades. As the impeller rotates, it imparts kinetic energy or velocity onto the water. By the time the water reaches the edge of the impeller, it has reached a very high velocity. This high-speed water flows off the impeller and into the balloon, where it hits the wall of the pump casing. This impact converts the velocity into potential energy or pressure. More water follows behind this, and so a flow develops. The volute channel has an expanding diameter as it spirals around the circumference of the pump casing. As it expands, the velocity of the water will decrease, resulting in pressure increasing. This expanding channel therefore allows more water to keep joining and converting into pressure. So the discharge outlet is therefore a higher pressure than the suction inlet. The high pressure of the discharge allows us to force the fluid through pipes and into a storage tank or around a pipe system. The thickness of the impeller and the rotational speed affects the volume flow rate from the pump, but the diameter of the impeller and the rotational speed will increase the pressure it can produce.
Alrighty. Hopefully you guys have all got the this little model up, and we'll just have a look at it. So you'll see that, cool. So as they kind of noted, the inlets are actually right at the center, right? So because it's a centrifugal pump, so it pumps. So essentially, you have that low pressure in the center, and everything gets spread out from there. So you have an inlet that connects to the atria of the heart. So I guess I should just clarify that when they have a total artificial heart, it doesn't actually mean that the atria and the ventricles are gone. They take out everything below the atria. So you think about the atria is actually a very useful collection point because it collects from a variety of different veins. And so you essentially just have to have one inlet each for each of the atria to connect it. And so the left-hand side here connects to the left atria, and then you have blood flowing in through there. And then on the opposite side, again, you'll see that it's in the center. Now, what's interesting about this is that it has one impeller that spins for both sides. So with the one rate of that impeller, it's able to maintain different pressures because, as we know, the right side of the heart has a much lower pressure than the left side. And so how does it actually achieve that? So if you look at the design of the blades, you can see the blades on what you've got on the left here is actually the right side of the heart. Those blades are a lot longer, but you can see that the kind of the radius to the edge of those blades is a lot smaller than the left-hand side. You can see that they all fit, like the right-hand side just fits inside this little circle here, right? So the radius of that side is a lot less, while the radius on the left-hand side is a lot bigger. So as they were kind of mentioning in that video, as the water moves towards the edge, it increases in pressure, slows down, and then it increases in pressure. And so through that, you're able to achieve different pressures on each side by designing the blades to be different. Okay, and so then the way that the blade is actually moved is by a motor. The motor is what we've got here, which is essentially a series of like electromagnets. And I won't go through exactly how motors work, but essentially you've got a series of magnets which are kind of pulling around our impeller in the center. Now, this is actually two motors that have been put together. So it's almost like if you have kind of, it's got 12, so if you almost have like six kind of electromagnets part of one motor, and you've got another 6 that are kind of set in between. And the reason they do this is they essentially have a backup. So if one fails, the other one will continue. And they have completely different electrical wiring. They're not connected in any way. They're completely independent. And so if one fails, the other one will continue to work. Now, one of the really cool parts about this design is that it has this here, which is a magnetic bearing. So a bearing is usually something that reduces the friction of a moving part. And in this case, in theory, it's supposed to completely reduce all of the friction, in that we've got what we call a maglev system, so magnetic levitation. So you have this impeller that's almost floating inside this casing, and that's due to the magnets that are holding it in place from the left-hand side. Now, at the same time, there is also some magnetic field that's also applied from the right-hand side, and so it kind of keeps it sitting in the center. And so through that, we end up having no wear essentially on the parts because there's no friction, because there's no touching. And so when you don't have any wear, it means it's really durable, so it can last for a long time. Okay, so if it's floating, that means there should be a gap around it, right? And if it's only one impeller, there's a gap around it, surely that would mean that there's blood flowing like from both sides of the heart, right? Because it's essentially one chamber that's mostly being split off by the impeller. So I guess my question is then, if there's blood flowing, which way do you think the blood would be flowing? Would it be from the left side of the heart to the right, or the right to the left? And think about the pressure on each side and which way fluid flows when you've got a differential pressure, so different pressures in either side. Any ideas? That's right, yeah, exactly. Because the pressure on the left is much higher than the right. It's kind of like almost having a ventricular septal defect, like a VSD, and you just get shunting of blood from the left to the right-hand side. And the genius of the design is that it actually wants to have that. And the reason is because if you have stagnant blood around the side, again, what do you get if you have stagnant blood? Clots, right? So you want to avoid clot formation around the edges of the impeller. And so they actually design it to have a decent amount of blood flowing around the sides. And so that's 1.5 liters per minute. And we'll say later that the output of the left and right sides should be the same. It's about 5 to 6 liters normally for a human. And this device is able to range anywhere from 3 to 12 plus liters per minute. But there is an additional 1.5 liters per minute that is going from left to right. Additionally, this gap here is large enough so that when the blood cells move through, you don't get damage to the blood cells. So they're actually designed to be slightly bigger than you'd expect, so that they don't want just a thin film. They want it to be big enough so that you don't actually hurt the red blood cells, and so you don't get hemolysis. Now, another really cool thing about this is that the flow control is not just through how fast the impeller is spinning. It's also through the ability of this impeller to move side to side. So let's just think about what happens there. So if it moves towards the left, so you've got all this dead space kind of where fluid isn't really interacting with the impeller. When you move it to this side, pretty much most of this fluid ends up interacting with the impeller. And so you actually get an increase in pressure coming out of the left-hand side. Well, if you move it the other way, the opposite happens. So you get an increase in pressure moving out the right-hand side. And so basically you can modulate the relative pressure coming out of the left and right side of the heart by moving it axially. And so and that is on top of how fast you rotate the impeller. So one thing you might have realized is that, okay, well, if you've got an impeller that's constantly moving, wouldn't you just get constant flow? And you're right, it would, in theory, just cause constant flow. And in theory, that might also damage some of the end organs, for example, the kidneys, the liver, maybe even the brain. And so the way they got around that is they're able to mimic pulsatility by varying the speed at which the motor is running. So they vary it between 1600 and 2400 RPM, and that gives a level of pulsatility. So you can actually feel someone's pulse, even if they've got this motor running inside them. So then to summarize, kind of like what are the main innovations here? So first of all, it's durable because it's got that maglev system. It doesn't have any of those surfaces in contact with one another. So it's going to last for a long time. Because of the big gap in the middle, it avoids hemolysis. It doesn't have any valves because you've always got constant flow. Even if it's speeding up and slowing down, you've got constant flow, so you don't have to worry about valves. Some of the older designs did have valves, but again, when you've got moving parts, you end up getting wear, especially like moving parts that are touching, you end up getting wearing down of it, and it reduces its durability. And it's got a backup motor. Remember, it's got the 2 sets of coils inside the motor. And finally, it's actually very small. So it can be used for an adult male, can also be used for a 12-year-old child. So it's quite versatile in that sense as well. And so as I mentioned, they're currently trialing in humans in Texas and up in New South Wales as well. And you might have seen recently on the news that it was used for a bridge to transplant in New South Wales where I think it was a man had this artificial heart for 104 days, at which point he then got a heart transplant. And so then I guess the next step for this device is that ideally they want to incorporate the battery and the electrical system inside the implant itself. Because right now, people who have this artificial heart, and pretty much any of those other devices like a ventricular assist device as well, they all have to carry around a battery pack and a controller, right? So ideally you have that inside the heart because you don't actually have to input anything into the controller. It all has algorithms that work out which way does the impeller need to move, how fast does it need to rotate. And so in theory, you can put that all inside the chest and you don't have to have those wires running out. Then the problem is, of course, how do you give it energy? So again, it would have the battery inside and ideally it would have wireless charging that would be able to maintain the power to the heart. All right. Thank you all. Do you guys have any questions before we finish up? Go for it.
Just with the battery pack in the wire, how do they prevent people from
I mean, I think that's more just during the procedure itself. They will put it in and then they will check for pneumothorax afterwards. It's the same with like certain central lines that you put in. Whenever you put it in, you always get a chest X-ray afterwards, just to make sure that you haven't got a pneumothorax. All right. Any other questions? No? All right. Can I please get you guys all to fill out this little feedback form? This is the first time that we're running this session, so we kind of want to know, what worked, what didn't work. Just please be honest. We just want to know what we can best do to make this session as interesting and as engaging for you as possible. And next week is going to be medical AI, and hopefully the week after we're going to be running something on surgical robotics. Alrighty, well, thanks everyone for coming. Thanks for taking Because it's quite small, it's quite low. Pretty much all the values like I don't actually know so much about the surgical side. I'd imagine as long as there's not too much free space around it, there'll be other organs like your heart is really good, just like to the vessel. There's also the lungs around it. Actually, in the pericardium, at least the inside layer of the pericardium is on the outside. So definitely, if it happens that way, then the coordination of the atrium and ventricle. So that's when you look put in a pacemaker to get the essentially do the function of the center. It's more that in the case that it doesn't work, the heart has a backup. You can at least get something pumping. Is really the most important part is the ventricle pumping. You get the atrium and ventricles keep pumping. It's still so the thing is, so there is actually, like, apparently I think 2/3 of the ventricles filling the atrium is passing. So it's really the atrium squeezing a little bit and it gets whatever remaining blood. But instead of thinking about, like, everything flows into the atrium and everything flows into the ventricle, it's really constantly flowing to the ventricle. And the atrium just makes sure the ventricle is full. No. I mean, they're both important. I said it's probably the most important. But you need to have an AV node but essentially, the AV node is just your backup to your SA node. But no one's going to have an SA node that completely stops working. It's going to be you still deteriorate, but you won't necessarily die because your electrical system, because your heart will keep pumping. Some of it just like it just because the electrical current is essentially it's like the movement of charged particles. So once it gets that's it just so the monoclonic medicine was that the lab is mostly so it's
There's probably some prerequisite knowledge that is going to know. So, like, for example, the way I got recruited as well, I did get into a programming course and I'm more interested in physical stuff. So I'm not actually doing any of the software AI stuff. Really, I'm looking at physical AI. So that's kind of my own. It's more of a yeah, and theoretically. Potentially. Yeah. So I guess this is more like a general question about doing research. This one's a little different because it's comparing generally the training of research is always up. You can also just directly reach out to various supervisors and often you'll start off with more like collecting data of this stuff specifically. Yeah, I mean, I think they you haven't had any
I think I just want to healthcare. But
it's kind of like it's quite informal. It's not like a very formal thing. To us, I don't know, because he recently moved to America. So she's going to be running it from America because it's so I don't know how it's going to work. But keep in touch. Maybe send me an email. And there's your
So we have 17 hours of time.
and just the rest of the month. Yeah, so we are always a stock. You can pull out like this.
Oh, yeah.
The original
that's so good for everything.
I know. We got Fulbright to go to America to study stents, and then did that. And you got to do 2 years there in the US.
Like, once I'm done with this,
Right, no worries. You guys want to?
I want to hear what they had to say about it because they literally said like we want to poach some of you guys, whether to do like research or they don't want to say there's some. Yeah, but yeah, they were saying like they're currently I think they're just trying to get through like something that they're trying to hold out as long as possible.
I mean, it won't be a problem as long as you get enough out. Because I don't think probably it's going the other way. If it's going the other way, then you've got the option of not going that side. And you've got, but you've got it going the other way.
Yeah, we just had a meeting for the company.
Yeah, I mean, it's, I guess, yeah, you're right.
It was
so
like
it's pumping out like 6 liters a minute, but then it's also pumping out.
And so there's another company that's like kind of doing stuff like that.
But it's efficient that it's only one.
So we just met with them. We just had a talk. We were kind of just sharing ideas. They were like, we kind of guys want to take some of your people and do that. Wow. Because they were saying like, yeah, because they basically are doing a similar moves towards like ideas, but they're like
yeah, I don't think that. The point is that it's not a problem. Like they actually want some blood to be constant, so they have that verification method.
For this one, just generally, this slide.
Yes, so
Thanks for reminding me. I need to pause this